Welcome! Today we're going to learn about points of inflection. So what's a point of inflection? Okay, so I've drawn a couple of graphs here. I eliminated the XY axes, but just look at the graph. In item 1, we have a curve that goes from concave up to concave down, if you look at the white shape. And if you notice there's a black point in the middle there, and that point represents the point of inflection. It's where our graph switches from concave up to down. It's also where we have a tangent line to the curve, and some textbooks do require say that that is a requirement as well. And then if you look at graph number 2, it's shaped a little differently, but again, you can see that at our point, we switch from concave up to concave down. It can also go the other way. It can also switch from down to up. It doesn't matter. The key thing is that we don't go from up to up or down to down. It has to switch from up to down or down to up. Also, we must have a continuous function on an open interval. So that is what a point of inflection looks like. So let's say we call our point of inflection C f of c, okay, where c is our x value and f of c is our y. Then if we have a point of inflection, the second derivative at c is equal to 0, or the second derivative does not exist at x equals c. So let's do an example. Many times you're not given a graph. If you're given a graph, it should be pretty obvious where the points of inflection are. And by the way, I didn't mention earlier, but I do have a video on concavity, so if you don't know what I'm talking about when I talk about concave up or down, I have a video that does explain that. So let's move on. Many times you're not given a graph, you're just given the function in algebraic terms as we are given in item 1. And so now when you're asked how to find the point of inflection, it may be a little more challenging. So since we know that if you have a point of inflection, the second derivative is either 0 at that x value or undefined, why don't we take our function and get our second derivative, set it equal to 0, and solve. So we go ahead and do that in steps 2 and 3. We factor in step 4, and in step 5 we solve, and our x values in this particular case are 0 and 3/2. So what we want to do is we want to see what's going on with concavity around these x values. So we want to check to the left of 0, to the right of 0, to the left of 3/2, and to the right of 3/2. And if we go from concave down to up or up to down, then we know we have indeed ourselves an inflection point. Right now, these are just possible inflection points. Okay, so in row 6, we create our intervals around these values. In row 7, we select test values at each interval. In row 8, we take these test values, we plug them into the second derivative to see whether we get a positive or negative result. If our result is positive, we know we're concave up. If our result is negative, we know we're concave down. Now, let's start with 0. What's going on with x is 0? Well, if you look at row 9, you'll see that to the left of 0, we're concave up, but also to the right of 0, we're concave up. So this is not an inflection point. If we take our second value, 3/2, and you look again on row 9, you'll see the interval to the left of 3/2, between 0 and 3/2, is concave up, but then if we do a test value to the right of 3/2, we find that we're concave down. So since we've moved from concave up to down, then 3/2 is indeed an inflection point. And if we look at our graph here, it's more obvious. If you look at 0, you can see it's just concave up. So, this is not an inflection point. But if you look at 3/2, our graph moves from concave up to concave down, so we do have a point of inflection. And that is our video on points of inflection. So now go practice, practice, and practice some more.